Welcome, my Gen Chem 2 class. Welcome to Unit 3. I'm so excited. This is one of my favorite topics, equilibrium. We are going to see equilibrium, I guarantee you, in some way, shape, or form in every science class after this. Equilibrium is such a big topic. In fact, in our Unit 3, we're just going to take equilibrium and get really good at it. And then we're going to continue it in Unit 4, very specific, with acids and bases. Our acids and bases are in equilibrium as well. So our equilibrium is actually 2 units and not just 1. So our goal in this first unit, I'm so excited, is to simply get to know equilibrium. Let's define it. That's our first video. We're going to actually just define our equilibrium in this first video. And then we're going to turn around and have a series of videos that just apply, and calculate. This is one of my favorite units because we're going to keep it small. It's very practical. You'll use the vocab from equilibrium and even maybe the calculations in almost every class of science after this. So I love it. Let's start by just defining equilibrium. What in the Sam heck is it and why do we care? So I gave 2, I'm trying not to give so many links because it's overwhelming. So I'm giving our textbook that we're using for OpenStax. Here is our section from our Adams First on equilibrium, and then just a little bit deeper in this one. But equilibrium is such a big topic. I know in my heart you could use the Google and find an equilibrium discussion almost anywhere. So let's take this video to define equilibrium. I'm so excited. Let's do it. All right, I want to start kind of where we left off in kinetics. I know y'all are looking at your tests and thinking about Unit 2 right now, and I'm so proud of you for starting Unit 3, even though our Unit 2 stuff isn't quite due yet. So let's picture a generic reaction, like we would write it in our kinetics section. And we looked at maybe just take a generic A plus B, and what if we make C plus D? All right, you'll notice right away I used a different set of arrows. These arrows are representative of equilibrium. They are telling you that this reaction is in equilibrium. And if you know a situation where a reaction is in equilibrium, you need to use these arrows. Okay, I love it. And then, of course, we don't forget moles. So in our general rate expression, we went ahead and included our moles in there. So what did we learn in kinetics? As a reaction starts happening, what can we see? What are we looking at? Well, we're looking at our concentrations of our reactants. They are going to slowly or fast, that's our kinetics section, but they might even start fast and then end up slow. We know they change. So those concentrations are actually going to start to disappear. And then as those are disappearing, what are you seeing on your product side? You are seeing your products appear. Okay, we learned that in kinetics. That's pretty straightforward. I like it. You start to see your concentrations go down in your reactants, and you start to see your concentrations go up in your products. I love it. Okay, now let's add a little twist to this. What if, what if your products could actually reform reactants? Now we're starting to get somewhere. And this is the very beginning of equilibrium. So let's write this out again. What if you're watching a change in your concentration of A and B? Okay, and they are disappearing. They are starting, and the second they disappear, you start to see your C and D appear. So now they are starting to appear. And now when you hit a magic concentration, so when you hit just the right amount of C and D, all of a sudden C and D can form A and B. So in other words, the reverse reaction can happen. And this happens all the time in nature. And the secret is you have to hit just the right concentration of C and D. And then A and B will start to form. So literally, your reaction can go backwards. Okay, now that's step number one. Okay, what happens if C and D can actually turn right around and reform A and B? Happens a little bit more than you think, so that can happen. And then now let's get just a little bit sassier. What if that rate of A to B happens at some rate, and we form C and D, and then holy cow, we hit that just the perfect concentration of C and D, and now our reaction starts to go backwards, and we start to make A and B. Okay, now wait for it. This will happen at some rate. Okay, let's get deep, and then we're going to get practical. If our rate forward and our rate backward are equal, we have a phenomenal setup where, how in the world would you have any idea? If you are literally disappearing A and B, right, at the same rate that you're turning right around and appearing A and B, how in the world would you ever know? So let's get practical then. So situation number one, your products can turn right around and make reactants. Okay, then we're going to add to it, what if the rate of your reactants forming products was the same as products forming reactants? So these rates now are equal. Holy cow, this is equilibrium. Now let's get a little bit practical. How would you even know that, and what would that look like? Well, let's think about it. At any given time, let's picture our reaction again. Okay, at any given time, let's put our little moles back in there. You've got A turning into B, or I'm sorry, A and B turning into C and D, and then you hit just the right concentration of C and D, and now they start going backwards and forming A and B. And if those rates are equal, what do you actually see? Well, just like in our kinetics experiment, we had to have something we could see. One of the easier things for us to actually see and monitor is concentration. So our concentrations of A, B, C, D. So what it would actually look like, it would appear that those concentrations have stopped changing. Okay, so let's picture this. You put A and B in a flask, your reaction starts moving forward. Awesome, we can judge that on kinetics, we can gauge that rate, we can start to see the appearance of C and D, and then all of a sudden, your reaction looks like it's done, it's stopped, but it stopped somewhere in the middle. It appears as though your concentrations have stopped changing. This is what equilibrium looks like. But equilibrium is very important. We've got a set of rules for our equilibrium. The first one is that you must have all species present. So literally you have some of A, B, C, and D. This is not to be confused with a reaction that goes completely from reactants to products. That is not at equilibrium. Equilibrium is a reaction that gets stuck in the middle somewhere. Okay, so we must have all of those they're all there. Okay. Number 2, equilibrium is actually dynamic, meaning it may appear that it's stopped, but it is not. You are literally caught in one massive balancing act. Your A and B is turning into your products, so reactants are turning into products, and products are turning into reactants. It is literally dynamic, and it is a balancing act. So it appears as though your reaction is done, but what it's reached is just the ultimate balance. You've hit the perfect concentration of products. Anything more than that reverts back to reactants. And then they hit the perfect concentration in reactants, and any drop more than that, and you're making more products. It is a cycle. It's kind of like windshield wipers, but really fast. This is dynamic. It is moving, but it looks like it's stuck, okay? And then just wait for it. Who sets up that balancing act? Is that balancing act up to you? No. That balancing act is not as simple as even 50-50. What if you have half reactants, half products? That is not what equilibrium means. In fact, you can have 1 atom of D in C and 1 billion atoms of A and B and still be in equilibrium. You just have to have all species present, and it has to look like your concentrations have stopped changing. It does not have to be 50-50. And that balancing act is literally set up by Mother Nature, and each reaction is different. Oh, don't you love to hear that? That's why this is a whole unit, and it's not just one example. So Mother Nature ultimately sets that balance. And each reaction is different. So any reaction that reaches equilibrium can reach equilibrium with all varied concentrations in their reactants and products. So we need a way to describe that. How do you actually describe equilibrium? How do you even study that? So what we're going to do is define an equilibrium constant. So let's go back to our example. And we've recognized now, we've studied this in the lab, and we've recognized, okay, this reaction can reach equilibrium. And how do we actually describe that? How do we define that? How do we tell our audience or tell the world, okay, when we reach equilibrium, this is what the reaction will look like? That is called an equilibrium constant. And since we're studying this big balancing act of how much reactants you have and how much products you have, our equilibrium constant is always written in the same way, and that is products over reactants. This is one massive constant, and what we're telling our audience is how much products you have in ratio or in relationship to reactants. And we're going to see our Ks in all kinds of examples. You will see a Ka, a Kb, a Kc, a Ksp. All of those big Ks are representing an equilibrium. They're all just for a different type of reaction. C is for concentration, A is for acid, Sp is solubility product, B is base, but they are all a KEQ. So don't be confused if you look it up and you see a big K, but it's got a different little subscript to it. So we're literally going to add math to this. We're going to calculate our ratio of products to reactants. That doesn't sound too bad, does it? But wait, there's more. We're going to include moles. Yay! And wait for it, this is the hard part following kinetics. Our mechanism, which we spent so much time looking at in our last unit, no. So we don't actually care about mechanism in equilibrium. We care about that place where the reaction reaches equilibrium, and we can describe that balance. Where does Mother Nature reach that balance? And do you have a lot of products or do you have a little products? Do you have a lot of reactants or a little reactants? So our K is a measure of that. So let's give an example and let's get specific. We're going to put our moles in, and then let's put some general relationships to numbers. So we're going to compare our products. But moles matter. So where do we put our moles? Okay, hold your seats. Don't watch this video while still doing kinetics. And if you do, that's awesome. I'm super proud of you. But write yourself a note. Wait for it. I'm going to put moles up here. That is not our reaction order. That is moles. So that is a really common mistake to goof that up. When you're dealing with kinetics, remember, we have to calculate those exponents. It's not moles. When we're dealing with equilibrium, we get a free pass. That's our moles. Okay, so then what do we do with our reactants? A and B. And we're going to put moles there. So put a box around this. We're going to write it in front of every single problem. This is our basic equilibrium constant, and we will use it in our calculations. Our first round of calculating will be to calculate our KEQ, and then our second round of calculating will be to use our KEQ and calculate our concentrations at equilibrium. We will go back and forth. This equilibrium constant we will see everywhere. We will use it quite a bit. Okay, so let's do one more round of defining, and then we'll pause this video and start another one where we actually start to calculate. Since these reactions can go backwards and forwards, we have to keep in mind what our K is telling us. So we have an equilibrium, even if it's crazy, for water. The formation of water is a ridiculous equilibrium, but let's write it. Okay, so if we write our reaction in this way, and this is our forward, we're taking hydrogen and we're making water. It turns out that our KEQ for this process then would be our water over H2O2. Okay, how do we look at that? Add your exponents. I love it. Now let me give you the value for this, and we'll see this again in Unit 4. It's actually staggering. Look at this. There is a known equilibrium constant for that. Holy crap, look at that. Okay, and I'm going to go ahead and say that that's at room temperature. Okay, so what does this number mean? Does that mean you have more water or more hydrogen and oxygen? This is what KEQ tells us. That number is huge. So that means that our equilibrium exists as almost all water. And you have the tiniest little bit of H2 and O2, but over here you have a phenomenally large amount of water. So the larger your KEQ, the more products. Okay, so the larger your KEQ, the more products. Okay, what about the opposite then? What if I wrote backwards, that backwards product? What if I want to go backwards from water? Let's put our moles back in. What would that KEQ look like? This time it would look like this. Now by the end of this unit, we're going to be writing these in both directions. So this is good practice. Put your exponents in. Now it turns out that there's a pretty basic relationship here between these two KEQs. And what is it? They are reciprocals of each other. So your KEQ going forward is actually the reciprocal then of your KEQ in reverse. So let's check out that number. I'm going to give it to you for free. Look at that, 2.9 times 10 to the negative 82 at room temperature. Now, doesn't this make sense to us? This is a phenomenally teeny number, meaning we have a ridiculously small amount of hydrogen and oxygen in equilibrium as products. So really, your KEQ, you can go forward and backward. They're reciprocals of each other. And you can really get an idea by a quick glance of your KEQ whether your reaction is going to favor products or it's going to favor reactants. It literally gives you that calculation of that ratio. So it's a really powerful definition that we're going to use every day for the next 2 units. So now that we've defined everything and defined our equilibrium, let's stop this video and let's start another video where we